Hey everyone, so I want to move on to the next part, which is conservation of energy. Now, this is actually the big bulk of this unit. It's actually probably considered one of the reasons why this unit can be difficult at times. This is where we actually apply everything that we just talked about in the previous parts, where we talked about all the different equations. The main gist of this, you should already know from your previous classes, is that energy is always conserved. Now, this means that energy can never be created or destroyed, it only changes forms. So if we have an object that has potential and then all of a sudden it loses potential, the idea is that it had to have gone somewhere. The object doesn't just lose potential energy, it goes somewhere. If we are looking at an object and we tally up all the different types of energies that the object has, and we find that before and after something happened, those energies are different, that means that we're just not taking into account another type. There's another type of energy that we weren't considering. Now, quick side note, it turns out that this actually isn't super appropriate. This is good enough for a lot of cases that we deal with. However, it turns out that as we start getting into the more nitty gritty physics, that energy can actually be created and destroyed. It's actually the conservation of energy doesn't really exist. It's actually energy mass conversion. Because if we end up losing energy, it could also be in the idea that we've gained mass in another form. So just kind of be aware of like if you go off into later physics and then you find out that conservation of energy isn't real, it's energy mass, and I don't want you thinking that I was lying to you. It's just that this is a simplified version that of cases that we're going to be dealing with most of the time, but technically at higher levels that's not always going to be the case. All right, so this is just an example that if we end up losing kinetic energy from an object, it's because it had to have gone somewhere. It maybe gone into the form of potential as the object went up into some height, raised to some height, or it could have been lost due to friction, due to heat. Uh, and oh yeah, so this is actually what I was referring to, is that energy could be converted into mass. So a lot of times this is actually considered energy mass conversion and conservation. So when you're dealing with this concept of energy, because we have to keep track of what the energy can be converted into, we want to ask ourselves is, where does the energy come from and where does it go? Basically, the idea is that we want to be very meticulous about keeping track of the energies at every point that the object is at. So if we have an object that is at the top of some ramp and then it goes to the bottom of the ramp, we want to keep track of what type of energy was at the top, what type of energy does it have at the bottom. And we want to kind of think about how is the energy changing as it goes from one point to another. So in the next few practice questions, what I want to try to do is I want you to try to think about what is the flow of energy. Where is the energy starting from, and what is that energy turning into? All right. So do that for these questions. So question 9. Pause video, work self, and we'll go over in a second. All right. Now, I just want to clarify that this is not really going to be something that specifically that you're going to be asked about on the AP. A lot of times, what they're just going to do is they're going to ask a problem. However, it's useful on your end to be able to kind of keep track of where the energy is coming and going. So here we have a ball that starts at rest on a table. It's lifted up at a constant speed and then dropped onto the table where it comes back to rest. So if we think about it, the object starts with zero kinetic and zero potential. It's being lifted up. So that term tells me that it is uh, there's work being applied to the object. It's being lifted up, which means that it's gaining, that work being done is being turned into potential energy. And then it's dropped. The potential energy is going to turn into kinetic energy as it falls down, and then it's going to come to rest, and so that energy is going to be lost to heat in the term of Q. So the flow of energy would be written as this: work turns into potential, turns into kinetic, turns into Q. Now, I'll actually mention something later on. So the next part, we have the ball starts at rest on table, lifted up at constant speed, dropped on table, bounces back up to the same height. So if we did the flow here, it kind of ends up working the same way, except once it turns into kinetic, because it lifts back up and it reaches the same height, the Q is no longer there. It's going to just go into UG again. So it goes from work to potential to kinetic to potential again. All right. You'll notice these part C is kind of very similar. So pause video, work self, and we'll go over in a second. All right. So again, here it's the same, pretty much similar to part B, except here when it bounces up, it's at a lower height. So instead of having it go straight back to UG, that UG is going to be different from this. So it's going to be UG plus a little bit of energy being lost to heat because not all the energy went back to potential. Otherwise, it would have went to the same height. Some of that energy must have been lost to heat. This is kind of what I was referring to before when I kept saying that you're going to use what changes to figure out the heat, that you're not using a specific equation. You might be using like the concept that, oh, energy changed by this amount, like it's not making sense. The energy that I started with and the energy I'm ending with are not the same. Therefore, you would realize that energy must have went into the form of heat. It must have been lost due to friction, even though they may not specify friction or energy being lost. All right, part D. Here we have solar panels. Now this actually will use some of the types of energies that we haven't talked about, but you kind of come up with the same idea. The idea is here is that it goes from solar to electrical to kinetic. So we get energy coming from the sun in the form of solar light. That solar energy strikes the solar panels. That solar panel then converts that energy into electrical energy, and that electrical energy is being used to power the blender, and the blender is spinning and turning. So kinetic energy. I think this last one. So pause video works out. I'll go in a second. All right, we have a block at the top, goes to the bottom. It's at a height. It's at the top of a ramp, so It's starting with gravitational potential energy. It doesn't have any kinetic energy. There's no one lifting the block or anything or applying forces, so there's no work. When it releases and it gets to the bottom, that gravitational potential energy is going to decrease and turn into kinetic energy as it moves. But because the incline is rough, some of that potential will also turn into heat being lost. So it's going to be UG turns into K plus Q. Now, the one reason why it's important to kind of keep track of this flow of energy is because one thing that we can do is say that since I know the gravitational potential energy at the top of the ramp will eventually turn into kinetic energy and energy being lost when it reaches the bottom, what I can then do is set these two equations equal to each other, and I can use that to figure out something. I can use it to figure out what the initial potential was. I could use this to figure out what the heat is. But the idea is that we would set the energies equal to each other once I know what this flow of energy is. So that's kind of one of the reasons why I talked about this and why I said it can be very useful for you to keep track of what the flow is in a problem, even though you may not be asked specifically to identify the flow of energy. Now, one thing to keep in mind is there's another type of energy that I need to talk about. It's called mechanical energy. So mechanical energy is referring to the energy that is potential and kinetic. Basically, it's energy that can be used in mechanics to move stuff. Uh, Basically, the idea is that it doesn't include heat. Um, and if there's no friction on the system and there's no energy being done in the form of work, so there's no one applying a force to it to add to the system or remove from the system, then what we can say is that the mechanical energy of the system is conserved. So the energy that it had before, the kinetic and the potential it had, is going to be equal to the final potential and kinetic that it ends up having at the end. Another way of writing this is that the amount of kinetic energy gained by the system is equal to the amount of potential energy lost by the system. So if the system loses 200 joules of potential energy, then it must have gained 200 joules of kinetic energy. Now, it is extremely important that you don't confuse mechanical energy with regular energy. Energy in its total form is always conserved, but mechanical energy is not necessarily conserved. It doesn't have to be. Perfect example is if I take a ball, drop it, it's going to hit the ground, and when it bounces back up, it's going to bounce back up at a lower height. That specifically shows that the object has lost energy. So the mechanical energy was not conserved in that bouncing. However, total energy was conserved because the amount of energy that the ball lost was equal to that difference in the height that it ended up having. If I took the potential energy that the object initially had and set it equal to the potential energy it ended up having at the end, plus the amount of energy that was lost, I would find that they were both equal. So keep that in mind that mechanical energy does not have to be conserved. It's sometimes conserved if there's just no friction and no work being done on the system. Uh, but total energy is always conserved. Now, if there is friction and there is work being done by being done in there, we can actually add those two into this equation. So this is kind of seen as more like the complete conservation of energy equation. You can use this in some problems where you just I basically the idea is that you're going through all the different types of energies. You're looking at what are the kinetics, what are the potentials, the work, the heat, all that, and you're setting the energies equal at two specific points. So at the initial point and at the final point. Now you may notice that I have work on the left-hand side and Q on the right-hand side. There's not a Q on the other and work on the other. And that's because of the fact that work is something that we usually start with, and Q is something that we end with. When energy gets lost in the form of heat, it can't ever be recaptured. So Q is a final point that the energy goes to. We can't get energy from it, but we can get energy from work. Just be aware of that. Now, the way I have this set up is that all these numbers, with the exception of work, will end up being positive values. So Q is going to be a positive, even though we're losing energy. These potentials and these kinetics should all be essentially positive numbers the way that they're set up. Now, you don't have to use this equation, and you're probably going to see me not really use the equation at all. The idea, again, is the easiest thing to do is just when you look at your 2 points, just ask yourself, what are all the types of energies at that point? And then when you look at the second point, look at all the energies at that specific point, and then you set them equal to each other. That's basically the idea that you're doing. That, in my opinion, is the easiest thing to keep track of. So what I wrote here is W is the work being added to the system. You could actually replace Q to be Q is the energy lost. You could also replace it as the work being done by friction. Again, sometimes this gets thrown in there where the frictional force is taking energy away. So you can actually figure out what the work being done by friction is and replace that for Q. All right. You'll see a few examples of that later on. So here's a first practice question. Pause video, work itself, and we'll go over in a second. All right. Now, one thing to keep in mind is when we're looking at all the types of energies, we have to be very specific and make sure that we don't accidentally include other types of energies. So here we have a tennis ball that's hit straight up with an initial speed of 50 meters per second. We want to know how high it goes. Now, if we go back to the flow of energy, the energy starts in the form of work, turns into kinetic energy, and then turns into potential. Now, if I wanted to figure out what the work was, there's nothing in this problem that allows me to do that. I don't know what the force that was hit with it. I don't know the displacement that that force was being applied to. So there's nothing I can do in this problem to figure out what the work is. So instead, what I want to do is focus on the other part, that at the very bottom, after it's hit, the object has speed. Therefore, it has kinetic energy. That kinetic energy is then going to turn into gravitational potential as it rises up. Therefore, I can say that the kinetic energy at the bottom is going to be equal to the gravitational energy at the top. Now, uh, so what I can do is take my two equations, the 1/2 mv squared for kinetic and mgh for gravitational potential, set them equal to each other. Turns out that the mass will drop out, and we end up getting this equation of height being equal to 125 meters. Now, two things that I want to point out is first, you might have realized that you actually could have solved this problem using kinematics. Kudos, that's actually one thing that you could do. Energy is one of those things where there are ways around using this concept of conservation energy. However, one thing that you're going to find out is that it's going to make a lot of problems significantly simpler when we go through the route of energy. The other thing that I want to mention is be very careful with conservation of energy. One mistake that I keep seeing people do is that they just set two energies equal to each other, but it's important to keep track that you're setting the energies at 2 points equal to each other. Note that when I described this, I said the kinetic energy at the bottom is equal to the potential energy at the top. There are going to be times where you're going to have a point that could have a combination of kinetic and potential. And a mistake I see people do is they look at this point that has kinetic and potential and they just set those two numbers equal to each other as if that makes any sense. What you do is you look at one point and you look at all the energies it has. You look at another point and look at all of its energies and you set them equal to each other. All right. We'll just do one more, but keep in mind that we're going to be doing a lot of this stuff in class. So here's the next question. Pause the video, work stuff, and we'll go over in a second. All right, so we have the pool cue striking the billiard ball, and it gives it some speed. So again, the flow of energy, it's starting with work being done because it's being hit. That work is then turning into the form of kinetic energy. And they want to know, they tell us what the average force is. So again, clearly we're going to do something with work. And they want to know what the distance this force is being acted on. So what I'm going to do is set that work being equal to the kinetic energy. So work equals K. Um, the work is going to be replaced with FD. Kinetic is going to be replaced with 1/2 mv squared. So I'm going to set them equal to each other and solve, plug my numbers in, and I end up getting a displacement of 0.0025 meters. All right.